Okay, so in the last video we ended on this example and we didn't finish it, so the reason for that, I was confusing this with a different example that I wanted to do. When I was working through this, I was thinking this is one of the, yet another example where the limit doesn't exist. This one, though, the limit actually will exist, and we were going to look at using the definition of the limit to show that. That's actually something I want to come back to later. So we're going to return to this example later. I do want to show that I finished this approach. We approached along y equals x to the 1/4 power. I chose that for the purpose of making a substitution here that would eliminate that exponent of 4. So we kind of saw that happening and how things simplified here. However, this still approaches 0, which you can confirm by using L'Hopital's rule. Notice if I substitute 0 directly, I get a 0 over 0 indeterminate form. So L'Hopital's rule, one application of that will actually make this limit doable, and you'll see that it still goes to 0. So typically, if you've tried a ton of different approaches and you keep getting the same thing, oftentimes that suggests that the limit might exist, but we want to approach it in a different way. So I think what I'm going to do is wait until the very end of this section to show you how to evaluate this limit. For now, let's move on to other examples. So far, the examples that we have completed have shown in both of those cases limits that don't exist. So it is kind of worth asking, how do we know when one does exist? And if so, how do we evaluate that? A lot of the techniques that you learn about in Calculus 1 for evaluating limits apply here. So for example, trying to simplify the expression that or the function that you're trying to evaluate a limit for will sometimes make it doable. So take this one for example. This expression right here, if I were to substitute 0, 0 in directly, becomes 0 over 0. So clearly I can't use that as a substitution. However, you may recall from algebra that this numerator up here, whoops, that's a y cubed, is a difference of cubes. And we have a technique for factoring those. Plus xy plus y squared. It looks like this. X minus y times x squared plus xy plus y squared over x squared plus xy plus y squared. That's how we factor that difference of cubes. And now we end up with this cancellation here. This is equal to x minus y. Okay, so in this case, after simplifying this, there's no domain restriction on this thing. I'm not dividing by something that could potentially equal 0. There's no real issues with this. So I can now substitute 0, 0 in directly. This goes to 0 minus 0, which equals 0, as xy approaches 0, 0. Simplifying first made it so I could evaluate this limit using substitution. So my limit is 0. Okay, now it's a little bit difficult to do that because, again, this involves factoring polynomials, but they are polynomials in 2 variables. So, it may not be immediately obvious how to do that if you can at all, but in this case, you can. All right, let's take a look at the squeeze theorem now. So the squeeze theorem is something you learn about in Calculus 1. It's a method of evaluating potentially difficult limits by comparing the function that you're using to 2 simpler functions that will squeeze down on this function as you approach whatever x value you're approaching. This is the 2-variable version of the squeeze theorem. So if you're looking at a function g of xy and you're trying to evaluate the limit as xy approaches some number ab of that function, if you are able to find 2 other functions that bound this one, g of xy, in the sense that, let's call f one of them, if f of xy is less than or equal to g, and if h is greater than or equal to g, for all xy that are close to ab, within that little disk, like that graph that we showed at the beginning of this section. And if you happen to know that both of these functions on the outside of this inequality approach the same number as xy goes to ab, then they're going to squeeze down on g and force g to approach that number as well. Okay, so here's an example where the squeeze theorem it makes sense. We want to evaluate the limit as xy approaches 0, 0 of x to the fourth sine of 1 over x squared plus the absolute value of y. Notice we can't just plug 0, 0 in here because then we're going to be getting a 1 over 0 here, which we can't evaluate that. So what are we supposed to do with this? Well, let's see. If I were to start by focusing on this function, or this part of the function right here, sine of 1 over x squared plus the absolute value of y. Regardless of what I plug in for x and y, this thing is always going to be between -1 and +1 because that's the range of the sine function. For any value of x and y that I plug in here, as long as this isn't a 0 and undefined, I always get numbers between -1 and +1 after taking the sine of this thing. Okay, but if that's the case, I can multiply all three parts of this inequality by this x to the fourth out here so that the expression in the middle looks like the thing I'm taking the limit of. That gives me negative x to the fourth less than or equal to x to the fourth sine of 1 over x squared plus the absolute value of y, which is less than or equal to x to the fourth. And now if you notice, I have that compound inequality similar to what we see appearing in the squeeze theorem, the statement of the squeeze theorem up here. Okay, so the squeeze theorem says that once you've established this, take a look at the two outside functions, negative x to the fourth and positive x to the fourth. What's happening to these functions as xy approaches 0, 0? Well, negative x to the fourth will approach 0, and positive x to the fourth will also approach 0 as xy approaches 0, 0. Notice the fact that y is approaching 0 is not important because the y doesn't show up here, but x is approaching 0, which causes both of these functions to approach 0. So by the squeeze theorem, x to the fourth sine of 1 over x squared plus absolute value of y will approach 0 as xy approaches 0, 0. So there is our limit. This one had a limit, it existed, and the squeeze theorem was how we found it. Okay? There's another method that's sometimes useful when evaluating limits, specifically when xy is going to 0, 0, and if the limit exists, but the other methods that we've seen so far don't appear to be helping very much. We can convert things to polar coordinates. So here's the idea. If you are approaching the origin specifically, remember that as xy approaches 0, 0, we're focusing on values of xy that are within some small disk centered at the origin. So let's say that this is my xy right here. Okay, but regardless of where that xy is, in polar coordinates, I can convert that xy into an r theta, where r is some positive number. Now, yes, it is possible for r to be a negative number in polar coordinates, but we don't need to make it negative. We can always think of it as positive and just adjust our theta appropriately. So what is happening as xy goes to 0? If xy is going to 0, 0, then what's happening to r? Well, again, if xy, this point right here, is approaching the origin 0, 0, that's shrinking r down to 0 as well. But because we're strictly thinking of r as being a positive number, we can do even better and say that r is approaching 0 from the right, or from the positive side. Okay? The benefit of using polar coordinates is that when we're originally dealing with two variables, x and y, converting into polar coordinates makes it so we only need to deal with one variable, r. Notice the theta is not important, because regardless of what theta is, wherever this point xy is, As we shrink this disk down towards the origin, it's really the fact that r is going to 0 that makes the impact. It doesn't really matter what theta is doing. So let's see if we can apply this. We want to evaluate this limit here. The limit as xy goes to 0, 0 of x squared plus y squared times the natural log of x squared plus y squared. Usually, your clue that you want to convert to polar is, one, like we said, that xy is approaching 0, 0, but also if you're seeing expressions of the form x squared plus y squared, because the conversion to polar says that x squared plus y squared is equal to r squared. So again, the limit as xy approaches 0, 0 of x squared plus y squared times the natural log of x squared plus y squared is the same thing as the limit, if it exists, it's the same thing as the limit as r approaches 0 from the positive side of, this would be r squared times the natural log of r squared. Okay, now this you can't evaluate by substitution. However, notice if I were to write this slightly differently, the limit as r approaches 0 from the positive side of the natural log of r squared over r to the negative second power. This is one of those infinity over infinity types of indeterminate forms, which suggests that we can use L'Hopital's rule on it. So let's try that. That would equal the limit as r approaches 0 from the positive side. So here, what's this the derivative of the natural log of r squared? That would be 2r over r squared over the derivative of this would be negative 2r to the negative third power. Let's do some simplification here. This becomes the limit as r approaches 0 from the positive side of 2 over r. Let's bring that r down here. This becomes 2 over negative 2 r to the negative second power, or this is the same thing as the limit as r approaches 0 from the positive side of negative r squared after simplifying. And this is just a polynomial. I can make a substitution. This approaches 0. Okay, so we have a limit going to 0, and we evaluated it using polar coordinates because doing that switched it from a 2-variable limit to a single variable limit, opening up all of the techniques that I know from Calculus 1 for evaluating those types of limits. Okay, in the homework, there's a little section of problems that tells you use polar coordinates to evaluate this. So even though you can make that decision yourself on other limit problems, the homework gives you a little bit of guidance in that sense and says these ones are ones you should use polar coordinates for. Okay, a little bit left to talk about. So here is our definition of continuity, and it's the same, essentially the same idea as how we define continuity for single variable functions. A function f is said to be continuous at a point ab if the limit as xy approaches ab of that function is equal to f of ab. Again, this is how we think of continuity in a single variable case. It basically says that the limit of a function at a particular point is the same value. First of all, it exists, but it's equal to the same thing that we would have gotten by substituting this point in directly. Okay, we generalize that and say that f is continuous on some set D if f is continuous at every point in that set. So the nice thing about continuity is that when we're evaluating limits of continuous functions, just like in the single variable case, all that we need to do is just plug that number or plug that ordered pair in directly. And also what's convenient about continuous functions in the 2-variable case or the multivariable case is that the same types of functions that we already know to be continuous in the single variable case are also continuous here, namely polynomials. This is a polynomial in 2 variables. Polynomials are continuous everywhere. So for this, I don't really have to question, am I allowed to plug in these values for x and y, or do I have to do some clever trick? I know that it's a polynomial and is thus continuous, so I can just evaluate this limit by substitution. This would equal, I'm plugging 1 in for x, 2 in for y, so that would be equal to, let's see, 1 times 2 squared, that's 4, minus 2 cubed, that's 8, plus 2 times 1, that'd be plus 2, so this is equal to negative 2. Those are the best kinds of limits because there's really no work to do aside from plugging things in. Okay. Up until this point, we've been focusing pretty much entirely on limits of two-variable functions, but really the same idea applies to limits of functions of any number of variables. We still can use that same epsilon delta definition that we did in the two-variable case, just generalized to work in a multivariable case. But if we want to speak in generality, it's easiest to present that definition using vectors. If you remember at the very end of the last section in 14.1, I showed that if we're working with a function of n variables, then the input looks like an ordered n tuple for such a function, but it's easier to represent that input as a vector. It makes the notation simpler. So that's what we're doing here. If f is some function defined on a subset D of Rn, so this is an n variable function. Notice that things are bolded here. Then the limit as x approaches a. X and a are both bolded, implying that they are n-dimensional vectors. That limit of that function is equal to L if, for every epsilon greater than 0, there is a corresponding delta greater than 0, such that if x is in the domain of our function, then, now notice what this is, the magnitude of x minus a. That's the same thing as saying the distance between x and a. So this captures that distance idea. If 0 is less than the distance between x and a, which is less than delta, then the distance between f of x and our limit L is less than epsilon. So in other words, as we shrink x closer to a, f of x will be made closer to L. So you're not going to really be evaluating limits of functions of like several variables, but here's one example where we're doing a 3-variable function. We want to either evaluate this function or show that it doesn't exist. Now think about the difference here though. We're going to use the approach that we did at the beginning of this section, where we look at different ways of approaching the origin, because we're approaching 0, 0, 0 here. However, in 3 space, there's also infinitely many curves that I could use to approach the origin, but they all look like space curves. So, for example, I could approach along, say, the y-axis. That's like one way I could do that, right? What is the y-axis, though? Approach along... Well, the y-axis is the line at which on which x and z are both always equal to 0. And as a vector function, if x and z are always equal to 0, that's going to look like this. And y is going to be the only thing that the parameter matters for. So this is the y-axis as a vector function. Okay? So what I'm doing is I'm substituting these values in 0, t, and 0 in for x, y, and z. What happens to xy plus yz over x squared plus y squared plus z squared? Well, xy becomes 0t, which is 0. Yz becomes t times 0, which is 0, so my numerator goes to 0. X squared and z squared both become 0, and that leaves me just with y, which I'm substituting a t in for, t squared. This goes to 0 as x, y, z goes to 0, 0, 0. Okay, and you could see that if I approached along other axes, the x-axis or the z-axis, the same thing is going to happen. But again, remember, just because this appears to be approaching 0 along all of our coordinate axes does not mean that the actual limit is equal to 0. We may need to approach using different space curves. Now the key thing here is to try and take, if we're using this approach, to try and approach along some line that converts this 3-variable function down to a single variable function, and then I can evaluate it as the limit of a single variable function, like from Calculus 1. So what I'm going to try and do is approach along another space curve, approach along, but one that's not an axis yet still looks really simple. So what if we approached along this space curve, t, t, t. Again, remember what this is doing is just giving me substitutions for my x, y, and z. What would happen? Well, xy plus yz over x squared plus y squared plus z squared. I'm substituting t's in for everything. So this becomes t times t, or t squared. Y times z becomes t times t again, t squared. All 3 of these are t squareds. And then combining like terms, I get 2t squared over 3t squared, or 2/3. Notice this is a constant function, so it approaches itself 2/3 as x, y, z approaches 0, 0, 0. Okay? We get different limits here and here. So as before, that implies that the limit of the entire function just does not exist. Okay? So that's actually it for section 14.2. I do want to go back and look at that other example that we paused on, because I want to show how to use the definition, the rigorous definition of a limit to evaluate that one. But I think I'm going to do that in one last video. So we're going to end this video here.